Okay, we're looking for the maximum height that we can throw this muffin on the moon, knowing how high we can throw it on Earth. So this is really just free fall for both, right? Just we have a different acceleration. So, we end up with it not moving, and after it's gone, some height h, and during that time, the acceleration, if we have positive, the acceleration is negative g. The only issue is that the g is not the same on the two. If it's the same person throwing it, we can assume the initial velocity is the same. So we're going to try to compare the two, and we're going to try to compare the two via ratio so that we can save ourselves a lot of effort in terms of the time of plugging things in and things. So if we want to do the kinematics part first, for both of these I would use the expression Vf squared is Vi squared plus 2a, I guess delta y. And for both, the Vf is 0. The Vi is always the same here, and I can solve for delta y, negative Vi squared over 2a. And this is true both for the moon and for the Earth. So I can say like delta y moon is Vi, they're the same, so I don't need a subscript, 2a moon. And I can also do that for the Earth. Delta y Earth is negative Vi squared, no subscript because they're the same, 2 times the acceleration on Earth. And I'm going to make a ratio here. So delta y moon over delta y Earth is negative Vi squared over 2a moon over the same thing but for the Earth. And our Vi's are going to go away. Those are going to go. 2a is going to go. The fraction is going to flip because this is in the denominator of the denominator. That's just in the denominator. So that's a Earth over a moon, which is all well and good, but we don't know a moon. So I'm going to look at forces. So as the muffin is off the ground and out of the hand, force down on it is mg, or I can write it as g times the mass of the one object times the mass of the muffin over the distance from the center of the either Earth or Moon, whichever we're on. I can write it this way for both. The Moon and the Earth have different mass and different radius, so that's why you get a different gravitational force on the two. But if I write it the same way, then I can also use a ratio to compare those accelerations. So if I look at my F-net for the muffin, it's just GMM over d squared, which would give me the mass of the muffin times the acceleration of the muffin. So the acceleration of the muffin is g times the mass of either Earth or the Moon, depending on which you're on, divided by the distance, which is really the radius of either the Earth or the Moon, since we're near the surface of either. So again, I want to use a ratio. I can write this for the Moon, and I can write this for Earth, and I can divide. So the acceleration on the Moon, actually I'm going to do it on the Earth, since that's the order I want it. The acceleration Earth over the acceleration on the Moon is going to be g times the mass of the Earth over the radius of the Earth squared over g times the mass of the Moon over the radius of the Moon squared. The g's go away, and I can simplify, bring this rm squared up to the top. Mass Earth over mass Moon times radius of Moon over radius of Earth squared. And we know that the mass of the Moon is 0.012 the mass of the Earth, and the radius of the Moon is 0.27 radius of Earth. So I can plug those ratios in, and I will get 1 over 0.012, because the m Earths will cancel, times 0.27, and the r Earths will cancel, squared. So that's my ratio of acceleration on Earth to acceleration on the Moon. I can sub that in here and then solve for delta y. So delta y on the Moon will be delta y on the Earth times that acceleration ratio, a Earth over a Moon, which is delta y on the Earth times 0.27 squared over 0.012. And that ratio is about 6, so the gravitational acceleration on the Moon is about a sixth what it is on Earth. And multiply that by our initial 15 meters, so that's 91.1 meters.